Hello everyone, I'm Zhikang Chen from Tsinghua University. I'm honored to share our research on behalf of the authors. The presentation will revolve around three questions. First, what is the goal of our research? Second, what approach do we use to achieve our goal? And third, what performance can we achieve in the use cases? We start from the goal of our research. With the development of software-defined networking, programmable forwarding engines are becoming more and more popular, and pipeline is a typical architecture of programmable data planes. Classic pipeline architectures include RMT in 2013 and its improved version, Banzai in 2016. A pipeline has high throughput and low latency, but its flexibility is limited. For example, for multiple dependent primitives, each primitive needs to be placed on a different stage. When the dependency chain gets longer and longer, the pipeline has to make a recalculation. Another example is stateful operations that cannot be atomized. In order to avoid pipeline pauses, in this case, the state update also needs a recalculation. Such a recalculation can severely affect the throughput and latency of the system, not to mention the potential state consistency issues. On the other hand, RTC, that is run-to-complete architectures, such as Trio proposed in 2022, has better flexibility than pipeline. So, there is a choice for users: a pipelined chip or an RTC one. Each of the architectures has its own advantages. Some applications want a double advantage, but it seems that you can't have it both ways without a hybrid chip. You have to build a bridge between the pipeline chip and the RTC chip, and this bridge can only satisfy the requirements of the specific application. If you want to cross a river somewhere else, you have to build another bridge, which is a complex and frustrating work. To solve this problem, we need a hybrid architecture. Both pipeline and RTC exist in such an architecture, and we can use different architectures depending on the requirements of the applications. So, we also call it an application-defined forwarding engine. That is our goal of the research. In fact, many researchers have noticed these problems, and they have proposed some hybrid architectures. For example, Panic proposed in 2020, Sirius proposed in 2023, and Intel IPU also proposed in 2023. These architectures allocate programs to hardware. An application is split to a program on the pipeline and another program on the RTC cores, which are compiled and written to the corresponding part on the chip. So, does this meet all the needs of an application-defined forwarding engine? Our answer is no, because different applications have different hardware requirements. For example, Application 1 needs a 10-stage pipeline and 2 multi-core RTC processors, while Application 2 needs a 2-stage pipeline and 10 RTC processors. The existing hybrid architecture is a mechanical integration of pipeline and RTC, so the resources are the sum of the maximums, that is, a 10-stage pipeline along with 10 RTC processors. We don't think it's a satisfactory result, so we propose another aspect of application-defined forwarding engines. In addition to allocating programs to hardware, we also want to allocate hardware to programs. That is, there are some hardware resources on the hybrid chip, and according to the application requirements, these resources are allocated to the pipeline and the RTC. The number of pipeline stages or RTC cores depends on the application requirements. The challenge is twofold. First, how to organize the hardware resources. A well-known reconfigurable hardware is FPGA, but its poor performance is unacceptable in high-speed forwarding. We have to work on programmable ASICs instead. Another problem is that it is difficult for users to know exactly what their application requires. There must be a compiler here that can determine how many pipeline stages or RTC calls are required for the application. So we move to the second part. We propose an architecture named OptimusPrime to overcome the challenges we listed above. First, we use a transformable architecture called a transformable block as a basic hardware unit to be allocated to the programs. A transformable block can be transformed to either a pipeline stage or an RTC processor. The ability of transformation is like that of transformers, so we call this transformable architecture OptimusPrime. Just like a transformer, it has a pipeline form which is fast and has a high throughput, and an RTC form which is more flexible. Thanks to the introduction of transformable blocks, the pipeline and RTC become organically integrated, and the hardware resources become the maximum of sum. In the previous example, we only need 12 transformable blocks instead of 10 pipeline stages and another 10 RTC processors. We build a transformable block by looking for commonalities in functional units. On the left, there is a MAU or match action unit from IMT, and on the right, there is a RISC-V CPU with 5-level pipeline. It can be seen that 4 functional units appear in both architectures. This allows us to achieve the transformability by rewiring these components. It is worth noting that there are multiple function units of the same function in a pipeline to achieve parallelism. When we transform the pipeline stage to an RTC processor, the call bits can be assigned to individual cores. In our experiment, a MAU with a similar specification to Tofino can be transformed into 8 RISC-V cores, and a transformable block is reported to consume only less than 6% of additional resources. In order to connect the transformable blocks, we design 2 data paths with a principle of low cost. The first path is for packets with a simple processing. These packets leave the forwarding engine directly after passing through the pipeline. The other packets are sent to a specific RTC core for further processing. These 2 paths are linear, so we designed an interconnection network that is also linear, which means low cost and scalable. Here is our ring-based interconnection, connecting 3 MAUs and 2 RTC processors. Packets with a simple processing pass through the anti-clockwise path after leaving the pipeline, while packets requiring complex processing pass through the clockwise one. The outer ring is used to convey PHVs, and we also propose an inner ring for other data transforms. For example, when a core on CPU 1 wants to write a state on MAU 2, the signal will be transmitted along the green line. Once the hardware is connected, let's match it with a compiler. The compiler is very complex, so we will just talk about how it works. In a hybrid architecture, we want to avoid separate programming. For example, using P4 to write programs on the pipeline and then write C language on the RTC cores. Separate programming on a hybrid architecture means we must manually partition not only the software but also the hardware for different applications. To solve this problem, we add some C grammars to P4 and develop an extended version of P4 named P4X. The P4X compiler automatically partitions the user program to the pipeline and the RTC cores, along with available transformable blocks. The goal of the partition is to maximize the throughput in the worst case. It can be seen that the first data pass is always at the line speed, while the throughput of the second pass is related to two factors: number of cores and the time for one packet processing. We develop an optimization algorithm to solve this problem. Next, we will select 3 typical use cases to show how our architecture can satisfy requirements of different applications. Case 1. In-network aggregation. The distributed machine learning can engage the programmable network devices for in-network aggregation to accelerate the training process. The ATP scheme proposed in 2021 uses the pipeline interface-based switches. The limits of the pipeline make it only support a limited number of aggregation dimensions within one pass, and packets carrying more parameters requires a rescalation. The implementation on OptimusPrime retains the 4-stage pipeline for handling the ATP handler, and we allocate the aggregation task to the RTC cores. Here is the comparison for ATP goodput. There is a 20% advantage in the FPGA experiment, because one packet can carry more parameters on OptimusPrime. In our software simulations, this advantage can be scaled up to 50% because the port rate is no longer a bottleneck. It's also worth noting that because of the performance isolation between the two data paths, a mix of half ATP and half other traffic doesn't affect the goodput on OptimusPrime, while it will decrease by about 1/3 on a pure pipeline. The second case is about in-network caching. Traditional key-value queries always need to be done on the server, but with a programmable switch, these queries can first access the in-network cache. Only cache-missing queries are sent to the server. There is no doubt that hit ratio is a key metric of in-network caching performance. However, it is difficult to implement caching strategies on a pipeline. For example, ARU needs to maintain a linked list, which is not supported because it's a non-atomic stateful operation. So, existing strategies tend to approximate ARU. For example, P4 ARU, proposed in 2023, divides the cache into multiple ARU units of size 3. On the other hand, our implementation on OptimusPrime is a 2-layer cache. Direct mapping is used on the pipeline, while ARU is implemented on each RTC core. Experimental results show that our cache hit ratio is significantly higher than approximate strategy implemented by P4 ARU, and the traffic sent to the database server can be reduced by more than 40%. The gap with the ideal ARU strategy is also small. The third case is network function integration. Researchers have implemented a number of network functions on Arduino-based switches, such as firewalls and load balancers. These functions often contain long dependency chains, making them take up too many stages in the pipeline. In our experiment, we select 5 typical functions, which is SIM flood detection, general DDoS detection, load balancer, NAT, and heavy hitters. The 5 services consume 37 stages in total, and 3 times of rescalation is required, resulting in huge performance degradation. By allocating a subset of programs to the RTC cores, our architecture achieves a significant advantage in both latency and throughput. In summary, our research has two results. First, application-defined forward engine architectures can satisfy the diverse needs for different applications. And second, transformer blocks can be used to implement such an architecture. Thank you for listening.